Hello, everyone. Welcome to Systems of Linear Equations. The goal of this chapter is to study system of linear equations. And in particular, we want to be able to find all possible solutions of that system of linear equations, which we call the solution set of that system of linear equations. And in order to be able to compute that solution set, we're going to use the Gauss-Jordan algorithm, which is roughly speaking elimination, but on crack. And we'll use this very cute remark called the rank theorem in order to describe those possible solution sets, because we will see together that there's only three possibilities. The solution set of a system of linear equations is either unique, so there's only one solution, or there's no solution, or there's infinitely many solutions. And the rank theorem is a nice little trick that will allow us to see which one of the three cases we're dealing with. If we want to solve a system of linear equations, we should first look into what is a simple linear equation. So a linear equation with n variables or n unknowns, and when we have a lot of them, like n of them, we're typically going to be using the notation x1, x2, x3, x4, all the way up to xn. And then to be a linear equation, the only thing you're allowed to do to these variables is multiply them by coefficients, real numbers. And these coefficients are fixed and are defined in the actual equation, a1, a2, all the way up to an. So a1 is the coefficient for x1, a2 is the coefficient for x2, and all the way up, an is the coefficient of xn. And then you can simply combine these formulas by adding them together or subtracting them if you want, but normally the negative value of the subtraction is encoded in the sign of the coefficient. And then these terms, they will sum up to what we call the constant term, which is simply another real variable, also known, and we call that constant term in general b. So b is a real number, it's the constant term. So the difference between the coefficients and the constant term, the coefficients are multiplying the variables and the constant term is alone. And typically the standard form of a linear equation, we have all the variables on the left with their coefficient added together, and on the right we have our constant term. And just one special case of a linear equation, which is not super important now, but might as well introduce it since we're just defining a linear equation. If that b value is equal to 0, we say that the linear equation is homogeneous. Let's look at some examples of linear equation. So here's three examples of linear equation. The first one, 4x1 plus 5x2 plus x3 is equal to -1. So here we have three variables, x1, x2, x3. We have three coefficients, 4, 5, and 1, and the constant term is -1. So it's not an homogeneous linear equation. The next example, 5x plus 6y minus z is equal to 0. So our variables are x, y, and z. Our coefficients are 5, 6, and -1. And the constant term is 0. Because my constant term is 0, this is an example of a homogeneous linear equation. And then for the last example, we have x1 plus 2x2 plus 2x3 plus 4x4 plus 6x5 is equal to 1. So here we have five variables, x1, x2, x3, x4, x5. The coefficients are 1, 2, 2, 4, 6 respectively, and the constant term is 1. Very quickly, here's some examples of equations which are not linear equation. The first one, x cubed plus y squared is equal to 1. The reason why this is not a linear equation, it's because we have some powers for x and y, here part 3 and part 2. That's a big no-no. The next example, we have xy plus z plus 2w is equal to 1. So four variables, x, y, z, and w, all to the power 1. But the problem is that we're multiplying these variables x and y There's no product between two variables to be a linear equation. So this is not a linear equation because two of the variables are multiplying each other. If they were dividing each other, that would be also bad. And the last example, you cannot have anything disgusting like a logarithmic term, an exponential term, or a trigonometric term. So even if this equation is an equation of two variables with respect to x1 and x2, there's a logarithmic term. This is not a linear equation. So again, simply put, the only thing you're allowed to do to create a linear equation is take your variables and multiplying them by numbers known as coefficient, add them up, and they will sum up to a constant, the constant term. That's it. That's all. All right, the big definition of this chapter, what is a system of linear equations? So a system of linear equation, roughly speaking, is just m linear equations. So you just pile them up. Instead of having just one equation, you have m of them. You could technically say that one equation is a system of linear equation where in your system you have only one equation, but that's overdoing it. So in a system, we still have n variables. Those variables are still labeled x1, x2, all the way up to xn. And then we build our system the following way. The first linear equation is a11x1 plus a12x2 plus etc. a1n xn is equal to b1. So that's my first equation. My second equation is a21x1 plus a22x2 plus etc. a2nxn equal to b2. And you do this m times, m like mommy. Okay, so am1x1 plus am2x2 plus etc. amnxn is equal to bm. So here, all those numbers in front of those variables, in general, aij are the coefficient. And here, one thing to notice, the first subindex, the I here, is really for the number of in which equation you're in. So if you have a11, you know you're in the first equation. If you have a21, you're in the second equation. And the second subindex, the j, gives you the number of the variable you're in front with. So if you have, for example, here, if you talk about am2, we know that we're in the m equation because of the first index, and that coefficient is in front of the second variable. So here, your index a and j will vary. So for I, will vary from 1 to m because we have m equation, m like mommy. And then your j index, the second index, will go from 1 to n because we have n variable, n like Nancy. In the system, we have m constant terms, b1, b2, all the way up to bm. So here, instead of having only one constant term for one equation, we have m constant terms because we have one for each equation. So roughly speaking, we're just stacking a bunch of linear equation. And if in general, in this chapter, I'm referring to this general system of linear equations of m equation with n variables, I might just be using that little star logo instead of copy pasting this big fat, accolade of equation just to save some space. So every time you're going to see that star, I'm just talking about the general system of linear equations with m equations of n variables. To keep track of all those coefficients and constant terms in that system of linear equation, we're going to be storing that information using matrices because we are, after all, experts of matrices. So here's a nice and very important definition that introduces two matrices that are going to be used to study system of linear equation. So if you start with any system star, so remember star is for m equations with n unknowns, the first matrix is going to be built by using only the coefficients of that system. So that first matrix is called the matrix of coefficient associated to star. And that matrix is simply built by storing the coefficients of that matrix, of that system in that matrix. So the first row of that matrix will be A11, A12, all the way up to A11. The second row is going to be A21, A22, A2n, all the way down to the last row, the mth row, AM1, AM2, all the way up to AMN. So because we have m equation, that matrix will have m rows. And because we have n variables, we're going to have n columns. So that matrix A is a m by n matrix with real entries. What about the constant terms? Where do they go? Well, there's another matrix where we're going to be storing those constant terms. So here, the new matrix, the augmented matrix associated to our star system, and the notation is A augmented by B because the first n columns are going to be constructed using the exact same matrix A. So the first part is A again, but we add one extra column where we put all the constant terms B1, B2, Bm. So that new matrix, instead of having n columns, is going to have n plus 1 columns. We still have m rows because we still have like m equation. So the augmented matrix is a m by n matrix. And even if there's a bar and a line here to separate the coefficient matrix part to the augmented part, this box is a m by n plus 1 box. And the line could be removed, and technically this would be better notation. But if we know that we have a matrix that's been built from a system of linear equation, we like to remember that this matrix is an augmented matrix by putting that line between the coefficient parts and the constant terms. So one extra columns for the augmented matrix. And for any system of linear equation in this class, the first thing you should be comfortable with is creating the matrix of coefficient and the augmented matrix of that system. That's the starting point of a good analysis to study a system of linear equation. The ultimate goal when you have a system of linear equation is to find all possible solutions, also known as the solution set or the general solution. But what is a solution for a system of linear equation? Well, because we have n variable, a solution for a system of n equations with n variable is n real number. Basically, we're trying to find the numbers that fits in that equation. Because we have n numbers, we can just plug the numbers in the system and check for equality. So if you replace all the x1 by that number, let's say k1, all the x2 by a number, let's say k2, and all the xn by a number, let's say kn, if you do the actual computation of a11 times k1 plus a12 times k2 plus etc., a1n times kn, and you get b1, and then again, if you go A21 K1 plus A22 K2 plus all the way up to A2 and Kn, and you get B2. And if this works for every single equation, all the way down to the last one, AM1 K1 plus AM2 K2 plus etc. AMN Kn, and you get Bn, we have a solution. But it needs to work for every single equation. If one of them does not give you equality, that's not a solution. We sometimes call this solution a vector because you can store these n numbers in a matrix, in a column matrix. Of course, here I write transpose just to be able to lay it down, but normally a vector is a column matrix. So we also call a solution a vector that fits in the equation. But that's just technicality for you. What needs to be understood is that a solution is an n tuple of numbers that fits in the system, that gives you equality at every single line of your system. Another way to check if a vector or if n numbers is a solution of a system of linear equation is by looking at it in matrix form. If you take the coefficient matrix and you multiply it by the column vector k, and if you get, as a result, the column vector B, That's one way, maybe a creepier way, but that's one way to check if K is a solution of that system. So again, here just some terminology. So the set of all possible vectors, the set of all possible n tuples that fits in the system star is called the general solution. So when we ask you to find the general solution of the system of a linear equation, we're trying to find all those n tuples that fits in that system of linear equation. All right, the best way to assimilate all that notation and terminology is by looking at examples. So here's a system of linear equations with three equations and three variables. So the first equation, x1 plus x2 plus x3 is equal to 6, 2x1 plus 2x2 plus x3 is equal to 9, and minus x1 plus 2x2 plus 7x3 is equal to 22. The first thing we want to do is construct the coefficient matrix and the augmented matrix for that system. So here we go. So the first one, A, the coefficient matrix. If you read the coefficients of x1, x2, x3, for the first equation, we get 1x1 plus 1x2 plus 1x3. So we have 1, 1, 1. Then for the second equation, we have 2x1 plus 2x2 plus 1x3. And then finally, we have minus 1x1 plus x2 plus 7x3. That's my coefficient matrix. And then for the augmented matrix, A augmented by B. So remember, the first part is just that matrix A again. So 1, 1, 1. So you can just rewrite that matrix quickly but carefully. So 2, 2, 1, and then minus 1, 1, 7. And then we add an extra column with the constant terms 6, 9, and 22. And that's the augmented matrix. Nothing too difficult. Just read your thing carefully, but make sure those matrices are written down correctly, because if you start to do computations on A or A augmented and there's a sign mistake, you swap some numbers or did not write one of those numbers correctly, then for sure the rest of your computations are going to be poisoned by this mistake. How do you check if a specific triplet of numbers is a solution of your system? Like for example, here we want to check that the vector or the triplet 1, 2, 3 is a solution. The only thing you have to do is plug those numbers inside your system. So all the x1s are replaced by 1. All the x2s are going to be replaced by 2, and all the x3s are going to be replaced by 3. And what you have to do is check for equality. So if you look at your first row and your first equation, or first row, I guess it's still 1 plus 2 plus 3. Is that equal to 6? Yes, sir. So that works. 2 times 1 plus 2 times 2 plus 3, that's 2 plus 4. 2 plus 4, that's, oh my God, 2 plus 4, which is 6 plus 3, which is 9. Yay, I'm a genius. And then finally, minus 1 plus 2, which is 1, plus 7 times 3, which is 21. That gives me 22. So because we have equality in every single equation, so every single equation here, we have equality. The left side and the right side are equal. 1, 2, 3 is a solution of this system of linear equations. Next example, we have a system of two equations with three unknowns. So we have x1 plus x2 plus x3 is equal to 0. 2x1 plus 2x2 plus x3 is equal to 1. So the first thing we're going to build together is the coefficient matrix and the augmented matrix. So for the first one, the coefficient matrix, so we have again 1x1 plus 1x2 plus 1x3, and we have 2x1 plus 1x2 plus 1x3. That's my coefficient matrix. That's a 2 by 3. And for the augmented matrix, A augmented by B, we have, so I like to recopy my matrix, my coefficient matrix quickly, but carefully. And then there's an extra column with the 0 and the 1 coming from the constant terms of my system. And that new matrix is a 2 by 4. Now let's check if some of those triplets are solution of my system. So we want to check if the triplet 1 minus 2, 1 is a solution of my system. This will actually work. Why? If you replace all the x1 by 1, all the x2s by minus 2, and all the x3 by 1, you can double check that if you compute 1 minus 2 plus 1, that gives you 0, and 2 minus 2 plus 1, that gives you 1. Because we have equality in the first and in the second equation, this is indeed a solution. But you can have more than one. So for example, the next one, so let's check if the triplet 1 minus 4, 3, so that's a different triplet. Let's check that this is also a solution. So solutions are not unique in general. So again, here, you just plug your x1, all the x1, you replace them by 1, all the x2s now by minus 4, and the x3s by 3. And let's go, let's check if we have equality. 1 minus 4 plus 3, yes, sir, we get 0. 2 minus 4 plus 3, yes, sir, we get 1. So because we have equality in the first and in the second equation, we have another solution for our system. But not all triplets are a solution. For example, let's try and check if 2 minus 4, 2 is a solution. So if we put it in our system, so we're going to replace first every single x1 are going to be replaced by 2. Or hello, sorry, a little technical difficulty. Please stand by. All right, so okay, let's go. So 2, replacing all the x1 by 2, all the x2 by minus 4, and all the x3 by 2s. And now let's check for equality. So 2 plus minus 4 plus 2. Yes, we do get our nice little 0 on the right side. But when we try this again, so 2 minus 4, which is 0 plus 2. Oh no, this is equal to 2, which is not 1. So we're not getting equality anymore on the second equation. So because we're not getting equality on the second equation, so this is not a solution. So you cannot say it's partially a solution. No, it needs to be true for every single equation. So 2 minus 4, 2, no, you're not a solution of that system. Next definition is something that we talked about for a linear equation. When the constant term is 0, we have a homogeneous linear equation. When we have a system of linear equation and all the constant terms, b1, b2, all the way down to bm are zeros, this is an example of a homogeneous system of linear equation. If I have to talk about a general system of m equations and n unknown that is homogeneous, I'm going to use the double star instead of just having that big fat accolade of all that notation. So if I say let double star be blah, 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 you know it's m equation n unknowns and all the constant terms are 0. What's so special about homogeneous system is that one solution is super easy to figure out. So if you replace every single variable by 0, or if you try to check if the 0 vector is a solution, of course the 0 vector is a solution, because if you replace all the x1 by 0, all the x2 by 0, all the xn by 0, of course it does not matter what these coefficients are. When you're going to do the computation for the first equation, you're going to get 0. Same thing for the second equation and all the way down to the last one. So the n-tuple of zeros, the 0 vector, is always going to be a solution of this homogeneous system. And that solution is the obvious one. And the obvious one has a special name. We call it the trivial solution. Okay, so homogeneous system, there's always at least one solution, the trivial one. If you replace all the variables by 0, you get equality on every single row. Here's an example of a homogeneous system of linear equations with 3 equations and 4 unknowns, x1, x2, x3, and x4. So it's homogeneous because all the constant terms are equal to 0. Of course, the trivial solution, if you replace x1, x2, x3, x4 by 0 in every single equation, you're going to get equality. But you can also have other solution, other non-trivial solutions. And typically for homogeneous system, we're going to be finding a lot of solutions that are not trivial. So for example, the vector minus 1, 1, 2, minus 2, so the quadruplet or the fourth tuple of numbers, minus 1, 1, 2, minus 2, is a solution of that homogeneous system, because if you try it, so if you replace minus 1 inside your system for all the x1, if you replace all the x2 by 1, and you replace all the x3s by 2, and all the x4 by minus 2, you can verify that 2 times minus 1 plus 2 plus 2 minus 2 is 0. For the second equation, minus 4 plus 4 is equal to 0, and 6 plus 2 minus 8 is equal to 0. So we have equality on every single equation. So that vector, minus 1, 1, 2, minus 2, is a non-trivial solution for this system, this homogeneous system of linear equation. Nice. All right, for this first section about the definition of a system of linear equations, where we check together how to construct the coefficient matrix and the augmented matrix for that system. And we also check together how to check if a specific n tuple is a solution of that system. That's it. That's all. Bye-bye.